Welcome to the deep dive. Today we're digging into something really core about large language models, LLMs. How do they actually, remember the stuff they're trained on? You probably think, like I did, it's mostly repetition, right? Seeing the exact same text over and over.
Yeah, that's been the standard view for a while. Verbatim memorization. The model sees identical sequences repeatedly, and that's how it sticks.
But there's some really fascinating research challenging that now. We're looking at a paper, The Mosaic Memory of Large Language Models, and it proposes a whole different kind of memory, not just from exact copies, just LLMs piece things together from similar but not identical bits of text.
They call it mosaic memory.
Right, and those similar bits, fuzzy duplicates.
Exactly. It's a really important shift in thinking. Instead of just, copy pasting, it suggests models can integrate information from these slightly varied fragments. It's much more complex.
Totally. And for you, the learner, getting this nuance is, it's crucial. It gives you a much sharper, more up-to-date picture of how these tools actually work. It challenges some basic assumptions, about learning, memory. It's pretty surprising stuff.
It really is. And this isn't just a small detail. It goes right to the heart of how LLMs handle these huge data sets. What's especially great about this research, I think, is the innovation in their methods, how they actually showed this.
Absolutely. That's a big focus for us today, the academic rigor here, the innovative findings that are really pushing things forward. Okay, so let's unpack this mosaic memory idea more. The paper argues pretty strongly against relying only on exact repetition to explain memorization.
Right. And the innovation here is moving past just counting identical sequences. They're saying, look, we need a better framework to grasp how these models encode and recall information.
And mosaic memory is that framework, the ability to build a memory from these bits and pieces, the fuzzy duplicates. You used the analogy of a mosaic artwork earlier, different tiles making a picture.
That's a good analogy. The model isn't just storing perfect copies. It seems to be capturing patterns from these near duplicates, these fuzzy ones, and reconstructing information from those fragments. This ability to generalize from partial matches, that's really the innovative insight here about LLM memory.
So, okay, the big question, how did they actually demonstrate this? How do you measure something like mosaic memory? It sounds tricky.
Yeah, and this is where their methodological innovation really shines. They set up this clever framework using something called membership inference attacks, MIAs. And they used these on specially designed synthetic data points, which they called canaries.
Canaries, like a canary in a coal mine, detecting something.
Exactly like that. These canaries are designed to tell you something about the model's training data, specifically what it's memorized. So they created these artificial sequences, the canaries, and then this is key, they generated fuzzy duplicates of them.
Ah, okay, so these fuzzy duplicates are the crucial part. They're like the original canaries, but deliberately messed with a bit.
Precisely. They introduced specific controlled changes, things like swapping out some words or tokens, inserting random tokens, even shuffling the word order. These are the fuzzy duplicates, similar, but definitely not identical.
Okay, got it. So they put the original canaries and these fuzzy duplicates into the LLM's training data. Then what?
Then they ran the membership inference attacks. And MIA basically tries to figure out if a specific piece of data, like the original canary, was in the training set. By seeing how well the MIA works, they could measure how strongly the LLM remembered that canary. Now, MIAs themselves aren't new, but applying them this way, specifically to quantify the effect of fuzzy duplicates, that's the innovative step.
Right. Okay. So the MIA tells you if it's memorized. But how did they link that back to the fuzzy duplicates causing the memorization?
Ah, that's where they introduce another really clever metric, the exact duplicate equivalent, O rho. It's basically a way to quantify how much memorization impact a single fuzzy duplicate has compared to an exact duplicate.
So MIA equals 1 means a fuzzy duplicate is just as good as an exact one for memorization.
Exactly.
And rho equals 0 means it has a lot of effect at all.
You got it. Rho equals 1, same impact. Rho equals 0, no impact. This metric is really central to their whole quantitative analysis. It lets them put a number on mosaic memory.
But what kind of rho values did they actually find? They tested this across several big name LLMs, right?
They did. The results were pretty striking and consistent, too. They looked at Meta's Llama 3.2, Microsoft's Phi 2, Google's Gemma 2, and GPT Neo from Eleuther AI. And the key finding, really quite remarkable, was that fuzzy duplicates where only 10% of the tokens were replaced.
So 90% the same.
Right. Even those contributed significantly to memorization. Row values were between 0.50 and 0.60. The innovation is quantifying that so clearly. Even small changes leave a strong memory trace.
Wow, okay, so half the impact of an exact duplicate, even with a 10% change. That's substantial.
It really is. And it didn't stop there. Even when they pushed it to 50% token replacement, half the sequence changed, they still saw measurable memorization. The row values were lower, sure, around 0.15 to 0.19, but definitely not zero.
Still measurable.
Still measurable. It strongly backs up this idea that LLMs are actively using these partial overlaps.
And I think you mentioned figure 1 in the paper shows this visually, like a graph.
Yes, exactly. Figure 1 plots this out clearly. You see row decreasing as token replacement increases, but it's a gradual decline, and it happens similarly and across all those different models. It really visualizes the robustness of this mosaic memory.
Okay, besides swapping tokens, they also looked at other kinds of fuzziness, right? Like adding noise or shuffling words.
They did. Those experiments gave even more insight into how this mosaic memory works. First, they tried inserting random irrelevant tokens between the meaningful parts, the engrams, of the original sequence. Let's call that A insert.
Okay, like adding junk words in the middle.
Right. And surprisingly, it didn't disrupt memorization that much. For example, putting one random token between every 20-word chunk, the row value was still high, around 0.84, much higher than you'd expect if it only remembered exact continuous sequences.
Hmm. So it suggests the model can kind of filter out the noise or look past it.
That seems to be the implication, yeah. It suggests an ability to identify and link the shared meaningful engrams even when there's noise mixed in. It's like it focuses on the overlapping signal. Figure 2a in the paper shows this robustness.
Okay, what about shuffling? That feels like it would really mess things up. A shuffle, I think they called it.
It definitely had a bigger impact, yes. They measured the amount of shuffling using something called Kendall-Tau distance, and they found memorization is sensitive to word order. Row drops quite a bit, even with minor shuffling. But, and this is interesting, even with significant shuffling, some information based on just the shared words, the vocabulary seems to be retained. Memorization didn't drop to zero.
So the exact sentence structure matters, but isn't everything. Even scrambled words retain some memory.
It seems so. Even when the engrams were heavily shuffled, the row value stayed above the baseline. It suggests the model holds on to some association just based on which words are present, even if their order is jumbled. Figure 2b illustrates this. It's quite a nuanced picture of memory.
Definitely. Now, this next point seems really crucial and maybe the most surprising finding you mentioned. Is this mosaic memory driven by the words themselves, the syntax, or the meaning behind them, the semantics?
This was, I think, one of the most innovative and potentially counterintuitive findings of the whole study. Their results point very strongly towards mosaic memory being predominantly syntactic.
Syntactic, so based on the overlapping words.
Yes, much more about the specific tokens overlapping than about any shared meaning those tokens might convey.
Wow. Okay, that kind of goes against intuition, doesn't it? You'd think understanding the meaning would be key to remembering something.
That's exactly the intuition they tested, and very rigorously. They ran experiments comparing random token replacements to replacements that were semantically similar, meaning they kept the meaning roughly the same, but used different words. They used Roberta to help find those similar words.
Okay, so replacing car with automobile versus replacing car with banana.
Sort of, yeah. And what they found was, well, the semantically similar replacements did lead to slightly higher memorization than random ones, but the difference was really small. The big driver was just having overlapping tokens, regardless of semantic connection. The syntax, the actual words, seemed much more important.
So using synonyms didn't trigger memory nearly as much as just reusing the same word, even in a slightly different sentence?
That seems to be the gist of it. And they hammered this point home with another experiment using paraphrasing. They got powerful instruction-tuned models like Llama 3AB, Mistral 7B, even GPT-4o to paraphrase their original canaries.
So same meaning, but totally different wording and structure.
Exactly. And when they tested the memorization of these paraphrases,
Let me guess the row values were low.
very low actually, despite preserving the meaning perfectly well, the memorization was way down compared to the simple token replacements. It's strong evidence that token overlap syntax is the main engine driving mosaic memory, not semantics. Table 1 in the paper lays this out clearly. It's a novel and really significant insight.
That really does shift how you think about what LLMs are learning or knowing. It's more pattern matching on the surface level.
It leans much more in that direction than perhaps we intuitively thought, at least for this type of memorization.
Okay, so if these fuzzy duplicates are the key mechanism, the next obvious question is, are they actually common? Do we see lots of them in real training data?
Crucial question for the real-world relevance, absolutely. And the researchers looked into this. They analyzed a huge data set called Slim Pajama. What's important about Slim Pajama is that it's already been cleaned up and deduplicated at the document level.
Right, so they already tried to remove redundancy.
Exactly. You'd think it would be pretty clean. But even after that process, they found a ton of fuzzy duplicates still lurking in there. They used Levenstein distance to measure similarity, basically, how many small edits it takes to change one sequence into another.
And the numbers were big.
Quite striking. They gave an example. If a sequence had 1,000 exact duplicates, it might have thousands more fuzzy duplicates close by, like 4,000 more fuzzy duplicates just 10 edits away, and over 20,000 more that were 50 edits away.
Wow.
Yeah, figure 4b shows this explosive growth. The number of fuzzy duplicates just balloons as you allow for slightly more difference. It shows these near duplicates are absolutely everywhere.
Which really underscores how important this mosaic memory effect could be in practice, which then leads to, well, how good are our current tools for cleaning data, our standard deduplication methods?
That's the next logical step, and a major concern raised by this work. Typical deduplication often looks for exact matches or uses n-gram overlap, finding identical long strings of words, like, say, 50-gram deduplication. If two texts share a 50-word sequence, one gets tossed out.
And the paper suggests that's not enough to catch these fuzzy duplicates that drive mosaic memory.
Their analysis suggests exactly that. While these methods do remove some redundancy, maybe even some fuzzy duplicates, they leave behind a lot of these impactful fuzzy ones. Figure 5 shows this pretty clearly for Slim Bajana. Even after 50-gram deduplication, plenty of fuzzy duplicates at various distances remain.
So current deduplication is leaky when it comes to mosaic memory.
It seems fundamentally limited in preventing these effects, yes.
And these leftover fuzzy duplicates can still contribute to the model remembering things it perhaps shouldn't.
Precisely. Which brings us to the broader implications, where this research offers some really novel perspectives.
Okay, let's talk implications. Privacy, model training, evaluation. Where does this take us?
Well, first, privacy and confidentiality. This is a big one. If models memorize via fuzzy duplicates, then sensitive data might be retained even if it's not repeated word for word. Slightly altered versions could still be memorized and potentially extracted.
So scrubbing exact matches isn't enough.
It might not be. We need to rethink data sanitization. Current methods might be insufficient. This calls for, innovative new privacy protection strategies tailored to this mosaic effect.
Serious stuff. Okay, what about just building better models, training efficiency?
Understanding mosaic memory could actually lead to innovation there too. If we know fuzzy duplicates are key to this kind of memorization, maybe we can develop smarter deduplication. Perhaps more aggressive syntactic deduplication, targeting these near duplicates specifically, could make training data cleaner and more efficient without hurting performance. Might even help it.
Less fragmented memorization, more generalization.
Potentially, yes. It could lead to faster training, cheaper models, and maybe better data mixing strategies too, beyond just avoiding exact copies.
Interesting. And benchmarks, how we measure if models are any good.
This is critical for the field's integrity, I think. Mosaic memory raises big flags about benchmark contamination.
Meaning the model might just be remembering fuzzy versions of the test questions from its training data.
Exactly. It could look like it's generalizing when it's actually just recalling near duplicates it saw during training. High scores, but for the wrong reasons.
And current decontamination, just removing exact matches, won't fix that.
Likely not fully. We need more innovative approaches to designing benchmarks and cleaning training data to ensure we're really measuring generalization, not just recall through fuzzy matches.
Right. That could really distort our view of progress. One last area mentioned was copyright detection, using those canaries.
Yeah, the canary idea for detecting copyright infringement is directly affected. If a model memorizes not just the exact canary sequence, but also fuzzy versions of it, it makes detection harder. It suggests we need, well, more robust canaries maybe, ones that are harder to break into fuzzy fragments, or better detection methods that can spot memorization even from these near duplicates. The innovation needed is in both the traps and the detection tools.
So across the board, this mosaic memory concept forces us to reconsider a lot of standard practices.
Absolutely. It reveals a much more complex memorization process than we assumed. It demands we rethink how we develop, train, evaluate, and even regulate LLMs. It's a paradigm shift, in a way.
Well, this has been a fascinating deep dive, really unpacking this mosaic memory paper. It's pretty wild to think about LLMs piecing together memories from these fuzzy, slightly AF duplicates. Changes the whole picture.
And the most striking part, for me, remains that syntactic finding, that it's so much about the words overlapping, not necessarily the deep meaning. That really challenges intuition.
Yeah. And for you, the learner, getting this more accurate, more nuanced view of LLM limits and abilities is just essential now, especially as these tools become more common.
Definitely, we need to move past simple ideas of memorization. This mosaic effect has to be considered in data prep, model checking, privacy, Everything. This paper provides a really solid, innovative foundation for that work.
Okay, so here's something to leave you with, a final thought to chew on. Given how common these fuzzy duplicates seem to be and how current deduplication falls short, how do we need to fundamentally change how we build training data sets and how we evaluate models? How do we truly account for this mosaic memory and all its implications for privacy, for fairness, for knowing if a model is actually performing well? And what completely new kinds of deduplication might we need to invent to handle this much more complex form of memory? Definitely something to think about. Thanks for joining us for this deep dive.